Welcome to the Advanced Lighting Design and Energy Code training video brought to you by the U.S. Department of Energy. You now can receive 0.10 CEUs towards ICC renewal certification and or 1.0 AIA CES learning units. However, in order to obtain AIA LUs, new AIA requirements dictated tests must be taken. At the end of this training video, you will be directed to a website to take the 10-question test, applicable to AIA members only. You must answer 8 of the 10 questions correctly in order to qualify for the 1.0 learning unit. BECP will report the AIA members who pass the test so credit can be awarded. A certificate of completion will also be available at the end of this training video.
Good morning and welcome to the Advanced Lighting Design and Energy Code webcast. I have a few house cleaning announcements first before we get started. As you know, this webcast is brought to you by the Department of Energy, and your speakers today will be myself, Eric Richman with Pacific Northwest National Laboratories, and Michael Lane from the Lighting Design Laboratory. And now we'd like to go ahead and start the webcast. Again, my name is Eric Richman. I'm going to be talking about some basics of the Building Energy Codes program, where there's some information and tools available, as well as some basics of the Energy Code requirements themselves. First of all, there is a website that DOE sponsors as part of the Building Energy Codes program that has a large variety of information and help dealing with energy codes, including some software tools. There's the website there up on the screen, and the tech support at BECP.PNNL.gov email where you can send in questions if you have them on energy codes or software tools of any kind. Just want to go briefly through what's available on the website and through this program. There are some compliance software tools available on the website that are downloadable and they're free for your use. There is a desktop software tool for commercial compliance called Contract. There's a complementary web-based tool, Contract Web, which allows you to do the same compliance, only doing it on the web instead of having to download a desktop version. There's also a Contract Package Generator, which will allow you to produce your own simplified prescriptive paths if you don't want to do the trade-off method in Contract Web or Contract Easy. There are also some printed materials for certain versions of the code, compliance guidance, prescriptive tables that you might want to use as well. Also on the website, there are training tools and PowerPoint presentations with notes, case studies, online training, online videos, just like this presentation I'm doing now. Similar presentations are available on the website on various subjects. There's also a very powerful resource center that has articles, graphics, tools, presentations, and videos on all varieties of subjects having to do with buildings and buildings energy. As an example of resource center capability, this is one search that was done on the Resource Center for just in the graphics area and just for depth system approach HVAC. And as you see, there are 92 different graphics out there available on different portions of that subject that you might find useful. That's the basics of what's on the Resource Center. I'd like to go now into the basics of lighting energy codes for those national codes that are available for states to adopt. As you know, you may know there are two major nationally available commercial building energy codes, ASHRAE ISMA 90.1 and the IUCC code. Both of these deal with commercial buildings, and both of them are available for states to adopt. The current published versions of these, ASHRAE IS in the 2004 version and IUCC the 2003 version with a 2004 supplement. Both of these codes do have previous versions that are adopted by various states. The code that you will have to use depends on which state you're in or which jurisdiction you're in and what code they have adopted. They may have adopted a brand new code. They may still have on their books an older version. It just depends on which one they've adopted. Some specifics about those codes. Both of the latest versions contain the new LPGs you may have experienced or heard about, the new tighter LPG values, but both in the 2004 and 2003 IUC, 2004 ASHRAE and 2003 IUCC. Both of these standards and codes provide minimum requirements for energy efficient design for commercial buildings. Neither of them, and this is important, neither of them is a design or advanced building guide. They are minimum codes or standards. And both of them cover all aspects of commercial buildings envelope mechanical lighting, water heating, power, and other equipment. There are some basic lighting code requirements, which is what we want to go over today. And they start with the major one, which is installed interior lighting power. And the requirement is that whatever lighting power goes into the building must not exceed the allowed wattage based on the code requirements. And there are, of course, some exceptions and allowances to that. There are also in the code mandatory requirements for control, individual space control, automatic shut-off. There's a bi-level switching requirement in IECC only. Both have exterior photocell time clock control. There are also some exterior lighting requirements, lamp efficacy in both codes, and in the ASHRAE code there are some power density limits as well, which we will go over in more detail. As mentioned, there are differences between these two codes. I'd like to cover those a little bit. In the IECC 2003, there is, as we mentioned, a bi-level control requirement, which is different from the ASHRAE code. IECC is generally a simpler code in that it doesn't have as much detail, and this was by design. Not that there's anything missing there, there's just a simpler version of the code. Part of that simpler version is that it has fewer exceptions in places such as the installed interior lighting power. There are 5 exempted categories of equipment, such as emergency lighting, whereas there are 15 in the ASHRAE code. The IECC code also offers an alternate compliance path using the ASHRAE 90.1 standard itself. The ASHRAE standard includes an extensive exterior lighting power list of lighting power requirements, which is not in IECC at this moment. Another difference is that it offers more space types than IECC. Again, IECC is a little simpler in that respect. The current ASHRAE code also offers some limited occupancy sensor requirements that are not currently in IECC. Let's take a little bit of time to talk about the main requirement, the installed interior power requirement. This is based on 2 different methods. One is the whole building method of compliance, where you look at your installed lighting compared to one single whole building lighted power density LPD value. Or you can do it on a space-by-space basis, where you look at the individual space types and associated square footages in your building and compare those with an individual space type LPD. In either case, the total requirement is that your installed lighting has to meet the weighted average or be less than the weighted average LPD requirement. As you're probably familiar, the LPDs seem to have been getting tighter in the past couple of years. And this may seem arbitrary, but the real basis for this is that the models that are used to develop those lighting power densities have had complete reviews in the last version of the standards, and that's why they have been tighter. It's not a random, arbitrary method. It's a review of the current technologies and basic requirements out in the real world. These include new illuminance recommendations from ISNA, some recent dirt depreciation research, a review of all the technologies, lighting, luminaire, efficacy that are out there, and a fresh look at current design practices. These are all inputs into the process, and they've just been reviewed. A little more detail on how these were developed, so people can understand where these lighting power densities come from. The current values were developed within the ISNA 90.1 committee with support and input from the ISNA Energy Management Committee. They have a basis in 4 basic items: current lighting products, performance data, lamp ballast efficacy, the latest IES light level recommendations, and some professional consensus to make sure that the models represent current practice. These elements are all combined into space models for each space in a building to calculate the lighting power density. And these space models are then applied to real building data to develop the whole building lighting power density. So we have both sets. The basis, again, one of the basic inputs are recommended light levels, and here you're looking at the lighting power density values, the recommended light level values from ISNA. And there's a 9th edition and 8th edition represented here, and what you're looking at, of course, are all of the different reading values. And these form the basis of the models, which we'll look at in a little bit more detail. What happens with these values is they are put into the models as the starting point, and the models look at two different areas, task area and general area. And in this example, the space is determined to be exactly half task and half general. The task area is considered to have a 50-foot candle basis recommended value, and the general a 20-foot candle value, and we end up with a total average weighted foot candle value of 35 for this particular example. We then go on to additional input, which are the luminaires that will be used to light the space. And each of the models is allowed to have up to 3 different luminaire types, and each is identified in its light use capability. In this case, the first luminaire is a linear direct indirect fixture, and it is going to provide approximately 75% of the foot candles for the space. There's a task luminaire at 15%, and there's a wall wash at 10%. And for each of these luminaires, the efficacy, light loss, coefficient utilization, and all these light loss factors are incorporated in each of the 3 luminaire types. And we determine the light delivery efficiency of luminaires, which directly drives the lighting power density or watts per square foot that's allowed in the actual models and therefore in the standards themselves. A final major input is a room cavity ratio choice. As you know, the geometry of the space will determine how much power is required to light the space according to the way it's designed. And for each of the models, there are 3 room cavity ratio categories. The lighting power densities are calculated for all 3 of these. And then, essentially by committee consensus, the appropriate room cavity ratio category for that space type is chosen, and the appropriate LPD for that becomes the lighting power density for that space type. Going on to look at what the results of that are, we have a comparison here between the previous version, 2001 ASHRAE in this case, and the 2004 ASHRAE. And as you can see in this percent change column, most of the values did go down. There was a tightening, if you will, of the requirements. But again, that's just based on a refreshment of all the different model inputs. With these values, and these are the values that you will see in the standard, this is an example of approximately 25 of the 100 or so models that were actually created. And you will see these in a selection of these in the standard. What happens at this point is, with the space-by-space models, we now have to generate the whole building models if you're using the whole building compliance method. And instead of, as in previous past year standards where a whole building value was chosen based on consensus, these were developed using actual square footage data from currently constructed commercial buildings, real building data. And a Dodge Construction database set of plans was used. Individual space takeoffs were done on these buildings. The current set is at 246 buildings, which makes up the database for developing these values. So it's based on some actual real building data. What happens is you assign these space-by-space LPDs to these square footages and calculate a whole building LPD. Another way to look at this graphically, here's one post office building. It's 17,000 square feet. It has all of these different space types, and they're represented adding up to the entire building. You apply a model LPD for each one of those, and you end up over here with a weighted average lighting power density for however many post offices there are. In this case, we're looking at 2 of them. That's the development of the whole building values. And to look at those, again, in comparison, there's the 2001 ASHRAE values and 2004 ASHRAE values. And again, as you can see, most of them went down. There was a change in 2001 to 2004 in that the hospital care category was split. And on average, everyone always wants to know what's the change. The average weighted change across the national building mix is approximately 25%. That doesn't mean that in every case the number for its two buildings is 25% more stringent, but on average that's what it turns out to be. An important part of the requirements in the standard are the exemptions and allowances, and particularly now that the numbers are perhaps tighter than they were before, it's important to understand that these do exist and to make full use of them. Both IUCC and 90.1 have exempted lighting lists. IUCC has a shorter list, 90.1 has a longer list, but the basic idea is that certain types of lighting, such as emergency lighting, is exempted from the calculation. You don't have to include it. And you need to look at whichever code is applicable in your state to realize what those are. Both IUCC and 90.1 also have interior lighting power density allowances, and these are very important, certainly in retail and other decorative applications. Some designs will need some allowances to show compliance. There are three basic allowances, one for decorative, which can be used in most spaces. A good example would be a chandelier, which is not part of the general lighting, but is there purely for decorative purposes. Another one that's currently in there is for the use of specific luminaires for computer screen glare issues. And the final one, which is probably the most important, is retail display lighting. And in this case, you get additional allowances, two different levels, depending on the type of merchandise or the type of lighting you're doing. The important point here is that these are only for the display area. You don't just skip them for the whole building. So you have to document where they're being used and make sure they are separately switched and only used for display. Another important part of the standard we want to look at are the exterior requirements. Both IUCC and ASHRAE do have requirements for these. The IUCC has a fairly simple requirement, and it's simply that exterior building grounds lighting, luminaires, equipment must be at least have an efficacy of at least 45 lumens per watt. The ASHRAE ISNH technical code has a similar requirement for building grounds lighting, but it only applies to luminaires over 100 watts, and the requirement is 60 lumens per watt unless exempted. But ASHRAE currently, the current version, has a much expanded list of requirements for the power use of exterior lighting equipment, which I'd like to go over briefly here as well. It's contained in a large table which has two sections. The first section are tradable exterior lighting power densities, and this means that all of these listed in the tradable section are similar to the interior lighting power requirements, in that you can take a total of all the exterior lighting and compare it to each of these areas times their square footage and trade them off. So, for example, you can use less in your parking lot and driveways and use more for your walkways, as long as your total is less than the square footage times the lighting power density weighted average. And there are a lot of the tradable values, which is part of them. There's another section, more tradable surfaces. Again, these are all tradable among themselves. The second part of the exterior lighting are non-tradable surfaces. The important point here is that these are use it or lose it. They cannot be traded with other areas of the exterior lighting. They are more specific in nature, facades, teller machines, gatehouses, etc. And they are either expressed, like the rest of them, in watts per square foot, or in this case, you have a couple that are specifically watts per a specific application. Again, these are non-tradable, use it or lose it. Those are the basics of the lighting requirements in both the IUCC and ASHRAE. And what I'd like to do now is turn the microphone over to Michael Lane, who will be talking about the advanced lighting design and ways to get more efficiency out of your lighting design.
Thank you, Eric. I want to remind everyone that you can send in questions at the bottom of your screen. You should have a section where you can add in a question at any time. So if you remember all those questions you already had for Eric, go ahead and put them in. My name is Michael Lane. I'm going to be talking about the energy design guide for small office buildings. A little bit about me. I'm not going to go through this, but a couple of highlights kind of towards the middle end there. I'm also on the 90.1 ASHRAE Energy Committee with Eric, and have been working with him for a couple of years on that, so I'm fairly familiar with it also. I'm also on the Lead Sustainable Sites Committee, so if anybody has any questions later, we can maybe talk about that. So the Advanced Energy Design Guide for Small Office Buildings, this is a guide. It's not a requirement. It's not a code. And it is specifically for small office buildings, 20,000 square feet or less. In the last couple weeks at the USGBC conference, The guide actually won Leadership Research Award for 2005, so that was really cool for the guide. If you follow the recommendations, again, recommendations are the key word here in the guide, you will result, your building will result in about a 30% energy saving reduction over ASHRAE 1999. Now, there's probably already a question in someone's mind, why ASHRAE 1999, not the 2001 or even the current 2004 standard? And the reason, as you can see on the screen, is that while DOE has worked with the 1999 version, and the states all have to meet the 1999 version, DOE is currently looking at the 2001 version. They may skip the 2001 version and go directly to the 2004 ASHRAE standard, just because it is already out. Again, when you get the book, hopefully everybody has a copy of the book. By the way, I don't make any money telling people to buy the book, and at the end of their presentation, you'll see where you can go to get copies of the book. If you follow the recommendations in there, you will get 30% energy savings. Important fact, this is one way to do 20,000 square foot office building. It is not the way. Energy savings was our independent variable when we were creating the book. Cost effectiveness was not the highest priority. So you will see some recommendations for some of those. Well, I'll call it state-of-the-art. It's not bleeding-edge technology. It had to be manufactured by these manufacturers. So the stuff that's out there, off the shelf. We also had a timely completion deadline. We started in October 2003, and we actually only had till about May of 2004. Then we gave it over, the committee gave it over to the steering committee and the publishers, and they got it published by February of 2005. It was a very quick, very quick process that was gone through to do this guide. Now, the guide is not just on lighting. It is a whole building. So if you go through this, you can look at what you need to do for your building envelope, of course, what you need to do for your lighting, your HVAC equipment, surface water heating, and then there are some additional bonus savings that were not included in the recommendations, but will take you past 30% or even further, depending on what you do with those. And some of those are, of course, exterior lighting, both facade lighting and parking lot lighting. And a big issue was plug loads, things like computers, things like fax machines, copiers, the office equipment that you have inside your building. And it was not done on just one specific region in the United States. It was actually modeled with the 8 different DOE climate zones. You can see the map in front of you, so you can kind of pick out where you are in the United States and which climate zone you're in. Now, the climate zones do cross the country. There's moist over here on the East Coast, dry, and then the marine. So there are some variables. So we actually modeled, I think there were 15 cities that were actually modeled to try to take into this consideration of the marine, dry, and moist climate zones. Here's an example of some of where that energy is used in the building, and looked at the base building and the advanced building. You can see here we started, one of the cities that we first modeled was Duluth. We also modeled Miami, Phoenix, and Seattle. Those were our first 4 cities that we modeled. Lighting, interestingly enough, doesn't change depending on where you're at in the United States. It always stays the same. There's no impact on heating and cooling, where you can see here that the cooling loads change depending on the region you're at. There's very low cooling loads in Duluth, very high cooling loads in Miami. That reverses when you get to the heating loads and so on. Plug loads all stay the same also, because again, those were a consideration that we took out. Originally, when we were first given the charge, we were to include plug loads in the 30% energy savings. We did some analysis, found out that, tried to find where our base was today. We got some industry data. The problem was saying, well, what would we say? 10%, 20%, 30%? It was hard to document it. So in the end, we took that plug loads out and having a bonus savings. It also helped us out because you see in Seattle, one of the harder areas to meet the requirements, which most people would think it probably wouldn't be. It's very benign, relatively environment. Problem is you have to have both heating and cooling equipment because you could switch one day from a cooling load to a heating load, wherein Phoenix and Miami you could really hammer the cooling loads, and then Duluth you could really hammer the heating loads, or heating savings. So we took the blood roads out and we met the requirements in 15 areas. So here are the 15 cities that we actually did model, and savings without blood loads all met the 30% energy savings goal. There were only 3 cities that didn't meet it if we did include plug loads, and that was basically getting no savings from plug loads. Now, when we get into lighting specifically, these are the base assumptions that are in the information that Eric already talked to you about of the ASHRAE Standard 1999. They are based on T8 electronic valves, the T8 fluorescent lamps with electronic valves. They're based on 1.3 watts per square foot, a lighting load in the office areas. They're based on an 8 to 5 Monday through Friday lighting schedule. No occupancy sensors are required in the 1999 standard, and no daylight responsive lighting controls are required in the 1999 standard. So that's the baseline assumption when we built our base building and modeled it. Those are the assumptions we used for lighting. In the advanced building, we used high-performance T8. I'll talk in a few minutes about what high-performance T8 lamps are. We went to 0.9 watts per square foot. The lighting power density was 0.9 watts per square foot instead of the 1.3. We modified the 8 to 5 Monday through Friday by using occupancy sensors in the non-daylight areas, in the restrooms, storage rooms, conference rooms. We did recommend daylight dimming control for the south and north perimeter zones only. And we also do recommend that you put your open office plans on the north and the south. It's the easiest to daylight, easiest to control the daylight with your small offices, your conference rooms, other smaller spaces on the east and west, where it's a little bit harder to control the daylight as it comes into the building, and use your occupancy sensors in those locations. The information you see on this slide here, where we've got a breakdown of corridors, office, other areas, lobbies, open office, private office, conference, and storage, are the information that we were to think back to what Eric was talking about, of when you take the specific models and you combine them with the Dodge data to find out what your total lighting power density is. This is kind of a simplified version of that, and in our Advanced Energy Design Guide, we had a space allocation of 10% of the floor area for corridors, 10% for other areas, which included restrooms and storage. And, actually, there's other storage down here, but restrooms, mechanical rooms, maybe a copy room, maybe a break room. Lobbies about 10%. Enclosed offices made up about 25% of the floor area. Open offices made up 20%. Conference meeting rooms 10%, and active storage about 15%. So if you take all percentages by the lighting power densities, come up with the 1.3 watts per square foot. In the advanced model, we stayed with the space allocations that we had before, but we changed the lighting power densities. You'll see that none of them match up to the 0.9. In the open office plan, it's 1.03. In the enclosed, it's 0.94. But when you do the multiplication of the floor space allocation by the light power density, you come up with 0.899, just slightly under our goal of 0.9 watts per square foot. Part of the reason that we went with 0.9 watts per square foot is that in the 2004 version of the ASHRAE standard, the lighting power density requirement for office space is 1.0. So we felt that we needed to go a little bit further than the current ASHRAE standard. So if you have the book or get the book, what you'll find towards the middle of the book is that there will be the 8 climate zones. And I'm kind of showing you a picture here of climate zone 4, which actually covers the area that I live, which is in Seattle, Washington. One of the real added benefits of this guide is that you can find what county you are in. We have all the counties here down below that fall into zones 1 through 8. The next page on there, you'll find a case study. The AIA, American Institute of Architects, was one of the sponsors to this project. I should have mentioned who the sponsors were up front. They were, of course, ASHRAE, the IES, the Engineering Society of North America, the American Institute of Architects, the Building Institute, and Department of Energy. The AIA went out and found a case study for each one of the 8 climate zones. Now, because they were found and built before the guide came out, they don't necessarily match the specific recommendations in the guide, but they kind of meet the intent of what the guide is all about. On the page facing that, you'll see this large table. And I don't have a big blow up of that. You see a little bit of it here, and we'll see a little bit of it on the next slide that just blows up the lighting section. But if you did have it in front of you, what you'd find is the first section is on envelope, the second section is on lighting, HVAC, and surface water heating. And then there are going to be specific requirements like on the envelope for the roof. And whether you're in a metal building, that's R13 plus R19. These are specific requirements. And so if you were trying to meet the requirements of this guide, it's prescriptive. There's no software like Eric mentioned, Concept. You're not going to use Concept to meet the requirements of this guide. You're going to go through here and say, I've got a metal building. The roof to the metal building, I've got the correct R value. Or the lighting, which we're talking about today, I meet the specific requirements of the lighting section. So you're basically going to create a spreadsheet. This is a blow-up of the lighting section to show you what we've got going on there. Lighting, of course, isn't just electric lighting. It's also the daylight that comes into the building. So we're talking a little bit about the vertical glazing also of 20 to 40% maximum window wall ratio, your thermal transmittance of a U value of 0.42, what your solar heat gain coefficients for the glass should be. This is a little bit of a confusing little section here, this window orientation and this calculation that you see here. What this is really trying to talk to you about in this calculation, I'm going to erase that so we can kind of just highlight the calculation, is that you want more glass on the north side of the building, south side of the building, than you want on the east and west. Primarily because it's easier to control from a daylighting standpoint, heat gain, heat loss, those summer sun angles on the east side, on the west side, it's a lot harder to control it. You might overheat the buildings and those kinds of time and stuff. So that's basically what this calculation is talking about. No glass, north, south. Skylights, 3%. ASHRAE standard will is in the 5 to 6% range. There's no specific recommendation on how you do it or what you do to control of that. Daylight, you're going to bring in the daylight can help us save energy. We can put photocell controls on the electric lights. We have that on the windows. So if we have skylights, we're going to want to put photocell control around those skylights to control the electric lighting in response to the daylight that comes into the space. We also have thermal transmittance and solar heat coefficient of those skylights. Lighting power density, again, there's the 0.9 watts per square foot that we talked about before. 90 mean lumens per watt. Instead of saying high performance TA branch, we put in the mean lumens per watt. Standard electronic ballasts, just as an FYI, there's some new electronic ballasts that have come out in the last year and a half. They really weren't out from two manufacturers at the time. when I did this, when we did this, and so we didn't use the second generation of electronic balance, but they will save you an additional maybe 7%, 5% energy if you're used to that second generation electronic balance. We are recommending that you dim the fluorescent fixtures within 12 feet of the north-south windows or within 8 feet of the skylights. If you put skylights in, you're going to need to dim them. Auto off all unoccupied rooms, so we want to put occupancy controls in all of the rooms so they can be shut off automatically. We do recommend manual on, automatic off occupancy sensors. So in a private office, the way that's going to work is you're going to walk in, the lights will not automatically come on. You will have to push the switch to get the lights turned on, but then it will go into the automatic mode. You leave the space, 5 minutes, 10 minutes, 20 minutes, whatever you have the occupancy sensor set for, it will then shut the lights off. Another important fact to consider when you get into these lower lighting power densities, 0.9 watts per square foot, or pushing the edge a little bit, is to keep the surfaces that you put in the space as highly reflective as possible. 80% plus reflective on the ceiling, 70% on the walls, and vertical partitions. It's very important that the vertical partitions in the open office areas are light colored above desk height. Now, the very far right-hand column, this column over here to the right, refers to the Chapter 4 of the Advanced Energy Design Guide. And so if I want to find more information on, let's say, the 90 mean lumens per watt, I could go to the electric lighting number 4, number 9, and number 17 in Chapter 4 and find out more information. And here are some of the things that we'll find when we go to Chapter 4. The recommendations for daylight controls. So we're going to dim our fluorescent lights in the open office areas, in the window wall areas where we have skylights. We really want to dim instead of switch electric lights off in response to daylight. We're going to get better energy savings, but primarily it's because of user satisfaction. If you're in the space, the lights go off, you notice that happens, you wonder why. If you're not educated on why they're going off, you might call up the maintenance staff and say, hey, there's something wrong with the lights in the space. If we dim the electric lights in response to the daylight, you'll never know that it's happening. It's very gradual, it's very slow, and you just will not see that. One of the other important facts, we want to locate luminaires parallel to the window wall so that they can respond to the decrease in light as it moves away from the window wall. We have more light next to the window versus 10 feet in, so we want to orient our fixtures parallel to the window wall. Task lighting, embedded into the ASHRAE standard models in open office and in private office, there actually is a small percentage of the lighting power density that is used from task lighting. We recommend using articulated task lights like this fixture here. The advantage of this versus the under cabinet fluorescent that most people put in because it's easy to specify with the furniture, if this one is user friendly, you can move it around. If you're right-handed, you can put the task light on the left-hand side so that the shadow moves away from you. Or if you are left-handed, you can put the task light on the right-hand side. A lot of times the under cabinet lights will be in the wrong spot and you can't move them. It's going to be in a situation where it may cause reflected glare on the task, a magazine that you're looking at. So we want to look at using the adjustable types of task lights. If you do use the under cabinet type lights, we're recommending hardwiring of the lower output of a 2-level ballast. So it's got a high level or low level, and you wire it to the low level. The reason you want to do this is that light's very close to your eye, and it's going to produce a lot of glare. The high-performance T8s, which I think we're going to get to in a couple of seconds here on another slide, they're very bright, and you have something that close to your eye, and it's going to produce some glare. If we can reduce that light output, we're going to reduce the energy. It's going to be more comfortable to the user who's sitting in the space. Of course, we talked about reflectances. This just shows you a little example of this picture here. shows you a little bit example of a very high reflective ceiling, a high reflective wall. In this example, at the bottom of it, it's showing you 28 foot candles. I don't have an image to show you, but if I were to reduce the ceiling reflectance to maybe the typical 70 to 80%, reduce the walls to 50%, reduce the floor even further, I might drop my foot candles in half just because the light's being absorbed by the walls and the ceiling. So we want to keep our reflectances as high as possible. So here we're going to talk a little bit about that high performance T8. What is it? It's a term you may not have heard before. You may, on the other hand, have heard of super T8s or premium T8s or high lumen T8s. Well, unfortunately, most of those terms that I've used are kind of the lamp manufacturers' proprietary names for some of the lamps, not just the lamps we're talking about here, but they'll use them in their literature. High-performance lamps talk about all of these. It is a lamp that produces more light, 3,100 lumens, so that's about 7% more light. It maintains higher lumens than a standard T8. It has really good color, so an 85 color rendering index, and additionally has a 24,000-hour life. Typical T8 fluorescent will only have a 20,000-hour life. Yes, there are some typical standard T8s that do have 24,000-hour life, but not all of them do. So if you go to this, you're going to get high light, and you're going to get longer life in your space. Now, you don't have to use, and there's some other options that you can use. So going back to the recommendations, the recommendation is just say 0.9 watts per square foot. High performance is what we use to model it, and it's one way to meet the recommendation. Occupancy sensors. I mentioned a little bit on occupancy sensors already, and so I'll reiterate some of that. Again, in private offices, we want to use infrared wall box sensors. You can be very, very careful, though, in those applications that the wall box sensor can see people's hands, because today's environment, we're all working on computers, and you're using a mouse a lot. If the occupancy sensor can't see your hands, your body won't move enough to turn the lights or to reset the timer inside the occupancy sensor. I actually did a little test on myself a few years ago in a private office. Set the occupancy sensor for 6 minutes. Lights went on and off on me all day. Next day I set it for 8 minutes, went off a couple times in the day. Third day, set it for 10 minutes, still went off on me once or twice, 12 minutes the day after that. I actually didn't have any of the quote-unquote false triggers. So I would recommend that you set your occupancy sensors for about 12 minutes. And of course, we want to these in non-daylit areas because there's no advantage of the daylight controls in those non-daylit areas, but the occupancy sensors will set the time. We'll save some energy. In this guide, we're recommending about a 15-minute time delay, so a little bit above the 12 minutes that I found in my test on myself. T5 fluorescent lamps, really hot topic these days. We should be using T5, T5HO specifically. Well, T5 and T5HO, they're a little bit smaller diameter fluorescent lamps. They have their place, even in office environments. A good application if you're going to use an indirect fluorescent light fixture where you're going to bounce most of the light off the ceiling. You have to be very careful because T5, especially the T5HO, have extremely high surface brightness, the lamp itself. So you don't want to be able to see the lamp when you're in the space. So if there's some kind of diffuser, some type of glass, some type of louver system below the lamp, so you're not looking at the lamp, it's okay to consider the use of T5. The initial lumens are about the same as T8 fluorescent high performance T8. Actually, the best one out there is standard T5. Very few people use standard T5. T8 high performance is going to come next, and then T5HO is actually a little bit less efficient than high performance T8s. And going back to the ASHRAE standards for a second here, in the models that Eric showed you, the standard fluorescent light fixture that's used is a direct, indirect fluorescent luminaire. That is the primary light source for both open office, and for private office, 75 to 80% of the foot candles are provided by this type of a luminaire. It's, there's a lot of different options out there for light fixtures. This was the committee consensus for a good energy efficient light source. It's going to provide good lighting in a space. There's problems if we use lens fluorescent fixtures on computer screen glare. There's problems if we solve the issue by using parabolic fluorescent fixtures, that they can cause high strain and glare in people's glasses and very harsh shadows. So there's pros and cons of all different types of light fixtures. You have to be a little bit careful of the totally indirect luminaires. They work well in a space, whether it's pendant mounted or the ever popular today copper type, the recessed indirect. They may not meet the desired light levels at the 0.9 watts per square foot, primarily because if you go over to the chart that I'm highlighting now, this bottom half of the distribution really isn't there. It's pushing all the light up into the ceiling if it's pendant mounted. If it's one of the recessed coppers, it's going to push it all into the fixture itself and instead of bounce out. It doesn't have that higher direct component that the direct indirect luminaire would have. So then we go back to the Advanced Energy Design Guide. Here's this chart we already saw that shows us the space types, floor allocation. So we now create a little guide that you can kind of see here on the right-hand side that looks at, in this case, open office and what you would do in an open office. In an open office, we want to maintain about an average of 30 foot candles. We would like to see approximately 50 foot candles on the desktop. And again, we want to daylight dim the lights within 12 feet of window walls on the north and the south side, and use occupancy sensors in other areas, all luminaires. Now, this is a little graphic that I created showing you kind of the layout, and it's going to be a little bit hard to see this, but I don't know if the highlighter will show up. The line I'm trying to highlight that's kind of red, that's my 50-foot candle line, and it goes over here again. So we're trying to get 50-foot candles on the desk, and it's coming close. We've got a few areas where we don't have the 50-foot candles on the desk, but we did pretty good. The average foot candles would be about 41, so our target was 30. We're actually achieving 41 average foot candles, doing an actual point-by-point computer simulation of the space, where the ASHRAE models are based on an average foot candle calculation or lumen method calculation. And this is a little bit of an example, a picture of maybe what the space would look like. Direct indirect luminaire is going to light the ceiling, which is going to bounce light onto the walls. We've got high reflectance surfaces on the partitions. Again, we don't want to get a cave. We don't want to get cave low down. We've also reduced the height. So this highlight I'm creating here, this partition, which in theory runs perpendicular to the window wall, the back wall in this picture, if there are windows on this back wall, that daylight's going to pass over the low partitions that are running parallel to the wall. We can run our high partitions with our cabinets perpendicular to the wall. And here we have the same thing for private offices. Here's my little diagram showing you what I need to have in there. I've got my little occupancy sensor. Of course, the book is a little bit bigger and easier to read. There's my occupancy sensor next to the door. Here's my work surface. So person sitting this direction, the occupancy sensor should see the hand movement. Target illumination, again, at 50-foot candles average, 50-foot candles on the desk. We're assuming that most of these will be on the east and west side, so we're not talking about daylight dimming here. We're just talking about using occupancy sensor controls for these spaces. And I've got two images coming up here to show you the layout and what happens if you take the under cabinet and the task lighting out, how important it is. If I just have my indirect fixture here in the middle and my direct indirect fixture here in the middle of the space, I'm getting 42 average foot candles. I've got levels as high as 80 on top of my desk. I've got levels way over in the corner over here of only 16, but hopefully I'm not doing any work over in that far corner. If I turn off the under cabinet lighting, you can see that the desk area here still has a good amount of illumination on it, but we're in the 40 range, 39, 34, 28, 20, all the way by the wall of about 17. So that under cabinet lighting and task lighting was very important to keep the foot candle levels on the desk. And that's where we need the foot candles. We don't need them throughout the space. An example of what that might look like, this little black square here is a representation of where I might have an articulated task light. There's another cabinet light here, and then of course my direct indirect fluorescent fixture, which is going to fall in the middle of the space. As we wait for the next slide to come up here, there it is. Here are the lobbies, and this again is one example of how we do the lobbies. We're only shooting for 10 to 15 foot candles average. If you do have, like we have here, a work surface, you're going to want to make sure again that we have 50 foot candles approximately on that work surface, and that's the design issue of where we put luminaires, put them over the work surfaces, so we get those highlight levels where we need them. Corridors, we're now dropping to around 5 to 10 average foot candles in the corridors. In this case, we're showing maybe two lamp 17 watt, one of those direct indirect, or actually one of those recessed indirect luminaires, about 8 to 10 feet apart down the middle of the corridor. Yes, you could use a 1x4 or a 26 watt compact fluorescent down the middle of the corridor in replacement of these recessed indirects and get enough light. What we want to do, very important in a corridor situation, is light walls. We don't need to light the floor. The light will get to the floor. We need to get light on the walls so again that the space doesn't feel like a cave. In conference rooms, we're now back to the 30 to 40 average maintained foot candles. Again, we want to use occupancy sensor controls. Here's my little layout for my conference room. I've got a light over the table and a couple other accent lights, wall washers to highlight maybe the presentation wall that's in the space. So it's very simple design, fairly low watts per square foot. In this case, we're a little bit above 1.02, but the average, again, goes back to the 0.9. We can have a few areas that are above the 0.9 recommended level, like the storage, 5 to 15 average foot candles. Our lighting power density is around 0.8, a little bit below 0.8 in our storage areas. This easily could be 2-lamp lens or 2-lamp recessed indirect luminaires in the space, because again, we want high level of light on the walls where the storage is going to be, but we don't want to use parabolics where we're going to push all the lights straight down to the floor. Other areas, about 10% of the space are other areas, and we're recommending about 0.75 watts per square foot. Again, the high performance T8, which ends up being about 1 luminaire every 80 square feet. Again, occupancy sensors or timers were appropriate. And these are going to be spaces like restrooms, electrical mechanical rooms, stairways, workshops, not conference rooms, but a break room, copy room, those types of spaces. Exterior lighting, again, one of the bonus savings is exterior lighting. Eric went through the ASHRAE recommendations for exterior lighting. Here we're saying limit exterior lighting power to 0.1 watt per square foot in the ASHRAE standard if you are building the grounds, walkway, pathway, those types of areas. It's 0.2 watts per square foot, so about half the lighting power density. In parking lots, the ASHRAE requirement is 0.15, so we're still 2/3 of the recommendation of the ASHRAE 2004 standards. And I was very involved in those numbers, and yes, you can do the lighting at these lower levels and still maintain good, adequate lighting, which is probably the most important thing to consider when you do go to lower light levels in exterior environments is don't just reduce the wattage, maybe add one more pole. Keep your lighting level as even as possible throughout the space. Because we're trying to, and because this was intended on just energy savings, we're recommending do not do decorative facade lighting. There's a lot of buildings out there most of them historic buildings that look really good when they're lit up. There's a lot of buildings out there that are new and even some older buildings that actually don't look very good when they're lit up. So be very careful about how you consider whether you want to throw light onto the building. That doesn't mean that you can't have exterior lighting at the entries that are lighting stairways. Those are important areas to light for safety and security issues. We're actually talking about the decorative facade lighting. Don't do that. Parking lot lighting shouldn't be significantly brighter than the adjacent street. Also, we don't want to create an adaptation problem. If the lighting in the surrounding areas is low, if you create a very bright environment, it will create adaptation problems when people move between those two spaces. So try to keep the levels close to what the surrounding areas are. Of course, use photocells or astronomical time switches to control the electric lights. We don't need those on during the daytime. When it's sunny, we want to get those turned off. If anybody's involved in LEED type projects, you probably know that LEED NC version 2.2 was just approved at Greenville last week or so ago. And one of the really cool parts is that if you're doing a 20,000 square foot office building and you want to get some energy points have always been difficult because you have to do a lot of modeling in LEED. But if you use this guide, option 2 says that you'll get 4 points by complying with the prescriptive measures of the Advanced Energy Design Guide. Again, it has to be an office building, less than 20,000 square feet, and you have to fully comply with the applicable criteria established in the guide. Basically, you need to go through to the page that I showed you, which is the prescriptive requirements, create a spreadsheet and say, yes, I needed this much insulation. Okay, this is how much insulation I put into the space. Here's my watts per square foot. I'm at 0.85. Good. All you have to do is do the spreadsheet that shows you prescriptively met the requirements. Where can you get this? Well, you can go to the ASHRAE website. It's good if you're a member, go to that member organization. You'll get a break on the price. The ASHRAE website. Here's a picture of the AIA bookstore. If you can read this, you can see if the retail price is $59. If you're a member, it's $47. Things can be true on the ASHRAE website, and of course, things can be true on the IESNA website. You can get it from any one of those 3 organizations. Please do. It's a nice little book. What's coming up? Well, we just started the second in the series. We're going to be doing one on small retail. We just had our first meeting 2-3 weeks ago. So we're about a month behind the process that the Advanced Energy Design Guide for small offices took. So if everything goes as planned, you should be seeing the Advanced Energy Design Guide for small retail out in January or February of 2007. Maybe the people who are producing it can work a little bit faster. Our deadline, I think, to get this to the steering committee, all the backup detail on basically everything you saw in the Advanced Energy Design Guide for small offices, same thing for small retail, is due sometime in the middle of June. So that's about a month behind the last process, but hopefully the production staff can be a little bit quicker.
This ends the training video. If you would like to take the test to receive AIA credit and or print a certificate of completion, please write down the URL shown on the screen. You will need to type this URL into your internet browser. Thank you.